So in this lesson, what I want to talk about is how Bohr looked at um, explaining the electronic or the absorption spectra of more complicated atoms, such as calcium here. So the idea that he proposed in relation to energy levels and electrons moving up and down to these energy levels explains, simple elements like hydrogen very well. There's only one electron, but what he wanted to do is try and apply this theory to more complicated atoms that have more electrons, like for example calcium, which has 20 electrons. So just a little bit of a quick recap. So what we can think about then is, so imagine this here is an energy level, and we have an electron that's hanging out here. Let's say we'll just write it as an X that's hanging out here in this energy level. What will happen is this electron will receive energy. So for example, this electron, which is part of an atom, it could be inside a discharge tube, and it might receive energy from the electricity that's passing through the discharge tube. Or another way is that this electron could be part of an atom and it comes in contact with a flame, for example in a flame test. So essentially what happens is we get an input of energy. Now imagine, let's say, so the difference, so this, when the electron is in this energy level here, it has a fixed energy associated with it. So let's say it's 1. Let's say the energy, when the electron is moving in this energy level, and we call this n is equal to 1 energy level. Okay, but it can be any energy level, and this is just so you can understand the concept. So the energy it has here is 1. Now, in order for it to get up here to this energy level, we'll call this n is equal to 2, it needs energy, let's say, of 3. Okay, so it just needs energy of 3. Now, the input energy has to be equal to 3. So for example, the energy that's coming from the discharge tube or the energy that's coming from the flame, it has to be equal to exactly 3. If it's equal to exactly 3, this electron will become excited. It will move up to this energy level and it'll hang out up here for a period of time. But if this energy, let's say, was 2, okay, it's not going to do anything. It won't excite the electron. So this idea that that there's distinct energy levels or a distinct energy value that's associated with each energy level is what's known as quantization. So when it then moves up here, let's say, so it has an energy of 1, it gets an energy of 3, and now it's up here. What will happen is it's in this excited state. It won't stay up there, it's unstable for a long period of time, and then what will happen is it'll spontaneously move back down to its original energy level. Okay, so it comes back down here. And then what happens is the energy that it had absorbed, let's say that energy was 3, that energy will be outputted. So the energy that will be outputted is 3. Okay, and that energy will be outputted. Now, what we can say then as well is that we can link these energy values to wavelengths. So imagine this is our energy that's coming in, and it's coming in the form of a wave. And let's say this wavelength is, let's say we call this wavelength 1. So this wavelength 1 carries the energy, let's say an energy value of 3, and therefore it will excite this electron. And then when it comes back out, it's emitted as a wave, and again it has that same energy value of 3 as well. So if this wavelength, let's say, changes, this energy value changes as well. And when the energy value changes, it changes whether it can interact with this particular electron in this particular energy level. So that's this idea. What we can do then is we can link in the wavelengths, so the wavelengths of the electromagnetic spectrum, with specific energy values, and they're also linked in with specific colors as well. Now, let's say this wavelength is 1. When this wavelength of 1, let's say when this light of wavelength 1 goes into a prism, what's going to happen is it's going to be diffracted at a very specific angle that is related to its wavelength. Let's say we have another wave that's coming in here and it has an energy value of 2, let's just say. It will be diffracted in a different way. The angle, the way that it's bent would be diffracted in a different way. And then what we can do then is we can shine these then onto a background, and this wavelength that has an energy value of 2 will show up as a band here, and this wavelength that has an energy value of 1 will show up, let's say, down here as well. And that essentially is what a spectra is when we look at a line spectra. Now remember, and so if we take, like, let's say, so this electron, or what we can say is this atom, this whole thing is part of a system which is an atom. So this can, when the energy comes in, it's absorbing it. So it can absorb energy, and then when it gives the energy out, it's emission. So the energy is being emission. So that's where we get these two different types of spectra. We can have a line spectra and we can have an absorption spectra. So an absorption spectra is if, imagine we have a gas of a particular element. So in this case, let's say calcium. So this is calcium in gas form. We shine, the input is white light. White light contains all of the colors of the spectrum in it. It passes through this. We then pass it through a spectrum, or pass it through a prism. And what will happen is you will get this continuous spectrum, but you will have these bands. And these bands or wavelengths of light have been absorbed by the calcium atoms in the gas that the white light passed through. Now, if you took this same gas, let's say, and you gave it sufficient energy, so you, let's say, heated it up, or you put electricity through it, this gas, the electrons will become excited in the atoms. They'll go up into a higher energy level, fall back down, and then it'll give you emission. And then you pass that through a prism, and then you get this type of setup here where you get like an emission spectrum. So, and this here, this prism here, so this just shows, so you have the light that comes in is what's known as the incident light, and depending on its wavelength, so this lambda function just represents wavelength, it'll be bent at a particular angle. And as this wavelength changes, this angle that it bends at changes as well. And that's how you can like separate all the different wavelengths of light onto a background. Now, what we want to talk about then is just if we think about, so Niels Bohr did a lot of his work in relation to explaining how, like, simple atoms like hydrogen that have just one electron, how they work. But if we take something like calcium, for example, so calcium is quite complicated. It has 20 electrons, and you can see here, if we look at this, so this is the emission spectra of calcium. It's quite complicated as well. You have loads of different wavelengths of light being bent when it passes through a prism. So you take calcium, you like heat it up in a gas like this, you pass it through a prism, and then you separate all the wavelengths of light that are being emitted by the electrons that are in the atoms of calcium, and you get this kind of a wavelength as well. And you can see it's very, very complicated. Like if we compare it here, for example, so this is the spectrum for hydrogen, which is quite simple. You know, you have these very simple bands that can easily be explained by, you know, by the movement of the electrons from energy levels back down. But if we look at, if we compare that to this, for example, to calcium, it's much more complicated, and things get way more complicated. Now, with the energy levels then, so when we're dealing with more electrons, each energy level, okay, so let's say this is our diagram of the atom. In the middle you have the nucleus, and then as moving out in these concentric circles outside of the nucleus, these are what are known as the individual energy levels. So you have N1, N2, N3, N4. And you can also represent it like this kind of a chart, where you have, so this is the N1, this first energy level, this is N2, this second energy level, and this is N3, this third energy level, N4, the fourth energy level, and so on and so forth. So this just continues on and on and on. And as you see, as we move out from, so as we start here in N1, and as the electron, if we move out here, the energy value increases as we move out further and further away from the nucleus. Another way to think about it is, in order for the electron to stay out here, it has to have, you know, a higher energy value to be able to stay out here stably within these energy levels. Now, what Bohr kind of started to discover was that within each of these energy levels, you can only have a maximum number of electrons within these energy levels. And this table here shows like how many electrons you can have in each of these energy levels. So he used this simple formula. So 2 times n to the power of 2, where n is the energy level. So for example, so 2 times 1 to the power of 2, that's equal to 2. So that's this first one here. So in the first energy level, so imagine this is our energy level. So I can have 2 electrons within this energy level. That's all that is allowed based on these calculations. That's all that's allowed within this first energy level. If we look at the second one then, and we can use our calculations again. So it's going to be 2 times 2 to the power of 2. So that's going to be 2 2s is 4, and then 2 by 4 is 8. So you have 8 electrons. So in this second energy level, you can have up to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 10. That's 10 of the 20 electrons. And then in this third, so in the third energy level, then you can have up to 18 electrons. So in the third energy level, calcium is going to have 10 electrons. So let's say 1, 2, 3, 4, 5, 6, 8, 9. Let's say 10. Okay, so it's roughly like this. Okay, now what's going to happen? So imagine then you have energy then that's coming in. So based on this simple formula, this will give you the arrangement of, or it gives you the limit, let's say, in relation to how many electrons can be in each of these energy levels. Now the same thing is going to happen. So imagine this is a cloud of atoms of calcium, and they have like an arrangement that's like this. So this is your cloud here, and you add energy into this cloud. So you either like put the calcium that's in gas form into a discharge tube and add electricity to it and add energy that way, or you take your sample of calcium and you put it into a flame, for example. So what you're going to be doing is you're going to be adding energy into the system. So what will happen is the electrons will start getting excited. They'll move up, depending on if they get the exact amount of energy that they need, they'll move up into a higher energy level, and then when they drop back down, they'll emit light of a specific wavelength that carries a specific energy value that is directly proportional to the difference of the energy level that it fell down from. So what's going to happen is, so imagine, so this is just, you're going to have billions of atoms that are all getting excited in different ways, let's say depending on the particular parts of energy that receive. But essentially imagine this is your atom here. So what might happen is, so this electron here might get some energy, it moves up to this level up here. This let's say this atom or this electron here might move up to this energy level up here. Then you might get, for example, this electron moving up to this energy level, and then so imagine that your energy is coming in. So you have your energy input through whatever means, through flame or through electricity. So the electrons are getting excited, they're absorbing these amounts of energy, they're going up into these higher energy levels, and then what's happening is they're going to then come back down again. So imagine it comes back down here, so this one is going to come back down here, this one will come back down here. And then what will happen is when it comes back down like that, they're all going to give off wavelengths of light. Or another way to think about it is they're going to give off energy. So these individual, let's say, wavelengths of light, or the light that they emit, then they'll go through a prism, imagine, and then they're all going to get diffracted at different angles. And then these different angles, so all of these different, let's say, each of these lines relate to a specific electron moving up to a higher energy level and then coming back down and then giving off a very specific wavelength of light that is bent in a very specific way, just like this, through a prism, and then it's being represented there on the spectra in very, very specific ways. So you have, just like this, you have electrons getting in energy, moving up to a higher energy level. They stay there for a period of time and they become unstable, and then they move back down and they give back out that energy that they absorbed. And then each time they do this, they emit light of a definite wavelength whose energy is equal to the energy difference between the two levels. So if we look here at this diagram here, so if I'm an electron, let's say in this energy, this N1, I need exactly the amount of energy. That's the difference between these two energy levels. That's the amount of energy I need coming in order to get me to move up to here. If I don't get that exact amount, I don't move. And then what happens then is when I'm up here and I come back down again, I'm giving off energy that is exactly equal to the energy difference between these two energy levels. And those energy values are directly linked. They are a specific wavelength of light. And that specific wavelength of light is bent by a very specific angle when it passes through a prism. So this light then, so these individual wavelengths of light that are being emitted by all of these different individual atoms, let's say within the atom of calcium, they're all being given off. And remember, this is just representing one atom. Like in a sample of calcium that's being heated up or being excited in a discharge tube, there's going to be billions of atoms, and they're all going to be doing this, getting excited, coming back down. And even within the atom itself, you're going to have different electrons moving up to different energy levels, depending on just how much energy particularly hits that particular atom. And then what you do is you see some of them like this, if you like, then these lines then are like an average of all of the different. So let's say like this line here could be created by 1 million atoms of calcium being excited up, their electrons being excited up to a particular energy level and then coming back down. And then the same here as well. So what you get then is the light appears as one of the lines in the line spectrum of the element. So each of these lines represent a wavelength of light, and each of these wavelengths of light represents an electron moving up to a specific energy level and then coming back down and giving off that specific wavelength or that specific amount of energy. So the line spectrum of each element then is unique to that element, because in atoms of that element, the spacings between the energy levels in terms of energy are also unique, and this gives rise to a unique electronic transitions. So because for example calcium has 20 electrons and they're arranged in a very specific way, that means that they will become excited and drop back down again to very specific individual energy levels that are unique to this particular arrangement of its 20 electrons. If we take an atom like hydrogen, for example, it just has one electron, so then it too will have very unique like patterns of the electrons becoming excited and coming back down that will be completely different to calcium. And then the same as well, if we have other elements on the periodic table that have more than 20 electrons or just less than 20 electrons, again, those electrons will be arranged in a particular way, and the electrons will become excited and fall back down in a very particular way for that atom, and it'll therefore give off very specific wavelengths of light for that particular atom. And those wavelengths will show up on a spectra in a very specific and particular way. So that's how, if you're to take this same principle and apply it to more complicated atoms, and Bohr's theory, that's how it would explain, let's say, why we get line spectra being created when we let's say, like, create the conditions for a line spectra for more complicated atoms such as calcium as well. So hopefully that makes sense. Now the Bohr theory of the atom, it was a mathematical theory. It worked well for like hydrogen atoms, and it did kind of run into problems when applied to atoms that had more than one electron. Now it's still, it's still a good theory, and it still gives a good explanation as to why we have like this kind of phenomena being happening and being created, and how that links into the electronic structure. And the important thing to kind of note as well is that it's this, let's say, this whole process that I've just explained, this is what enables us to see individual colors, let's say, in our environment. So if you think about when you look around in your environment and you're looking at objects that have a particular color, those objects are made up of billions of atoms like this. And what's happening is light or energy is being absorbed by those particular atoms. Some of the wavelengths of light are being absorbed by the electrons, and then by the atom, and then other wavelengths of light are being emitted by the atoms that make up that object. And those wavelengths will correspond to a particular color that is on the light spectrum. So we have all of the colors that are on the light spectrum, and that's actually what enables us to be able to even see the objects that are in our environment as well. It's all related. It all goes back to the electron and them becoming excited and moving back down. So essentially what's happening is you're actually sitting in a sea of atoms being excited by electrons being excited, going up to higher energy levels, coming back down, and then sending out that light. And light travels extremely fast. So this process happens so quickly that it doesn't even register. Everything just seems stable and continuous. But in fact, what's happening is this process is going on, this excitation of electrons to higher energy levels and back down. So hopefully that makes sense, and hopefully that explains in a little bit more detail when we're talking about energy levels and what that means. Okay, so thank you for listening.